In this lecture, we will examine another type of reactive intermediate, and these are electron deficient species, specifically oxygen electron deficient nitrogen and electron deficient oxygen. But last lecture, just as a quick review, we looked at carboanions, which are, as we mentioned, negatively charged, and they have an extra electron. And we looked at how to generate carboanions. They're typically made by reacting a alkyl halide with a metal, so making carbon more electronegative than the other metals, such as magnesium. You will recall the Grignard reagent. Another way of making carboanions is from an acid-base reaction, where the proton bonded to a carbon can be abstracted, but it has to be an extremely strong base. We also looked at reactions of carboanions, not as many as carbocations, but they do rearrange and are involved in different type reactions. In this presentation, however, we will look at, as I mentioned, electron deficient nitrogen. As you can imagine, it's going to be a nitrogen that's partially positive or fully positively charged. Next, we'll look at electron deficient oxygen. Same thing here. Looking at your periodic table, you will recognize that these two atoms are pretty close to each other, in fact, next to each other. And lastly, we'll look at reactions of these electron deficient nitrogen and oxygen species. Okay, let's begin. Electron deficient nitrogen and oxygen, as mentioned here, exist if there is a very polar bond to these atoms. And equally important, it has to be bonded to a very good, extremely good leaving group, as I've pointed out here. So let's look at this general representation here. Here's my nitrogen. It's a double bonded to carbon, but here is a leaving group, a very good leaving group. It's typically electronegative, so this bond here is a polar covalent bond where these electrons are closer to the leaving group, leaving this nitrogen partially positive. So this is an electron deficient nitrogen because it has here a nitrogen that's positively charged. Well, partially positively charged. Here we have an oxygen, and it's now bonded to an extremely good leaving group, which is also typically electronegative. So this polar covalent bond here, these electrons are closer to the leaving group than they are to oxygen, making this oxygen here partially positive and, as mentioned here, electron deficient. Okay, let's get into some more specifics here. So let's look again at electron deficient nitrogen. So here's an oxime, and here is, it's bonded to OH, the OH group. As you know, the oxygen here is electronegative. So this bond here is a polar covalent bond, but it is not a good leaving group. So OH negative here, as you will recall, is a very strong base. So it is not stable, not a good leaving group. But in the presence of an acid, H+, proton donor, it will be protonated, and now we have a much better leaving group, in fact an extremely good leaving group in the form of water. So here is our water right here, And if these bonding electrons go to make the water leave, you can see what's left behind is a charged nitrogen or an electron deficient nitrogen. The bottom line here again is that we need an extremely good leaving group for this to form. Let's look at another example here. And these type molecules are called azides. So let's look at this. It's a nitrogen that has here R groups or H's, and it's bonded to another nitrogen and a third. As you can see here, this looks like it could be nitrogen gas if these electrons came over. So that is an extremely good leaving group. Number one, because it gives a neutral molecule, nitrogen. And number two, because it's a gas, so it's entropy favored. Once these electrons break, or there's a heterolytic cleavage of this bond here, we have here our electron deficient nitrogen. Let's look at the electron deficient oxygen. Here is an oxygen. Here is another oxygen, but this oxygen is part of this leaving group here, the acetate. So if this bond breaks and the electrons go onto the oxygen here, we have this good leaving group here. And of course you will recall that this is also resonance stabilized, so we can put these electrons onto the oxygen here to get another resonance structure. So this is a very good leaving group here, and what's left behind from this heterolytic cleavage of this bond here is an electron deficient oxygen. Let's look at reactions now of electron deficient nitrogen and of course oxygen. So let's look here. We have a ketone. We react a ketone with hydroxylamine. We can get the oxime here. So that's how this oxime is made. As we mentioned earlier, this is electron deficient, but this OH is not a good leaving group because it leaves as OH minus in the presence of an acid, and of course the solvent here, water. We get an electron deficient nitrogen. But as you know, it's an intermediate, so it will not exist for a long period of time. It's not stable and won't be isolated. So the product is right here, the amide. But let's see what had to happen here. You can see now we have R and R prime bonded to this carbon, and over here in the product the same carbon now has one R group, and it appears that this R group migrated to this nitrogen here to get the product, and of course water is added. So this is the product, the rearranged product. It's known also as the Beckmann rearrangement. And so let's see what happens, or what should be involved to go from the oxime to the amide to get the rearranged product. So let's look at the mechanism. Here we have the oxime in the presence of an acid. We're going to protonate this to get a good leaving group. So let's go in this direction here. We get this as a good leaving group. Let's see what can happen here. Let's go here first. We can have loss of water to get this group here, or the electron deficient nitrogen, and we can have now a migration of R2 to R1 to get this. Or we can have a concerted migration while the leaving group leaves. So as the R group comes in, it pushes out the water. So we can go in this direction minus the water here while this R2 migrates. We call this a concerted migration with a loss of water. Or we can lose water first to get this electron deficient nitrogen, and then the water, and then we have here this migration occurs. It is considered that the preferred, it's been suggested and proven that the preferred route is right here. So it prefers to do the migration while this group leaves to form this intermediate here. Once this is formed, water attacks this carbon that's now positive to get this, and of course loss of a proton we have here, and after another loss of another proton here we have our amide. So again, the oxime converted to a good leaving group, a concerted migration while this leaves gives this species here in the presence of water. The nucleophilic water attacks this carbon to give this species here, still charged, loss of a proton here gives this intermediate, another intermediate here, and of course loss of the other proton gives the carbonyl here of the amide. Okay, as you can imagine, there are two possible migrations. So let's put two different groups on the oxime here. So we have a carbon, a methyl group, and a phenyl group. Now for the Beckmann rearrangement, the same rearrangement of the oxime in a acidic medium, it's possible to have both group migrating, not at the same time of course, but separately, which means that we'll have two possible products here. Let's do the analysis. So we can see this product here results in the phenyl migrating to this nitrogen. How do we know that? Here's the nitrogen and here's the phenyl. This product here results from the migration of the methyl group here. Again, how do we know that? Because this methyl group is now bonded to the nitrogen, this nitrogen in the product, and the phenyl is still bonded to the carbon. So we have two possible products. One, the phenyl migrates, the other one, the methyl migrates. The question now is which would be the major product? As you can imagine, the major product results from the reaction that gives the more stable transition state for the migration in the RDS. Right? So let's see which one would be more stable. So let's go here. If we have a migration in which the phenyl group migrates as this leaves, notice we're looking at a concerted reaction here where this migrates as this leaves. One step. That's why we call it a concerted reaction. If this happens, we have a transition state that looks like this, and notice here the positive charge is stabilized by the phenyl ring. So it's resonance stabilized. So the positive charge that results from this migration is stabilized by the phenyl ring here. So as you can imagine, that's pretty stable. Then of course the reaction goes on. Fast steps here, this would be the determining step. So the fast step goes on to give the major product because it's stable. Well, let's see why it's more stable than the other one. The other one here involves the methyl group migrating to give this transition state. As you can see here, this positive charge is not resonance stabilized, so it's not as stable as the previous transition state for the migration, for the concerted migration in the RDS. So what happens here is that since this is not as stable, it results in the minor product. So you should be able to predict the major and minor product of this type rearrangement, also known as the Beckmann rearrangement to the electron deficient nitrogen. So in this case here we have the mechanism. So this protonates here to get this. This migrates over to the electron deficient nitrogen here, and of course loss of water to get this intermediate, and of course not stable, so water attacks here, and we have the reaction continuing in a fast step to give this as the major product for the phenyl migrating to the nitrogen. The phenyl here is this phenyl that migrates to the nitrogen, and here's my nitrogen. Let's look at the other mechanism. Here is the same type protonation occurs, and we have this leaving group. Now we have a concerted migration of the methyl to this electron deficient nitrogen here, while this leaves as water. As we pointed out before, the transition state for this migration is not as stable as with the phenyl, but it happens. Then we have nucleophilic water attacks here, and it continues until we have this as the product, but this now is the minor product, because now you can see here the methyl has migrated to this nitrogen, which is this methyl here is now bonded to this nitrogen in the product. So that's the Beckmann rearrangement from the oxime. Let us look here on electron donating groups. So electron donating groups, if bonded to the phenyl ring. So here's the phenyl ring right here. We have electron donating groups bonded to it. Will that stabilize the transition state even more than the phenyl or less? Since it's considered electron donating, of course we know why, because these electrons here, or one pair of these electrons, can donate its electrons into the ring. So it's electron donating into the ring. As you can imagine, if this group here migrates, we have the positive charge here, and these electrons here can stabilize this positive charge even more than the phenyl ring, than a hydrogen, for example. So you can expect this to be even more stable than if it were just your phenyl group. And of course, since this is the slow step of the reaction, these other steps are fast to give this as the product. Let's look at electron withdrawing group. So here we have the NO2. You may recall the NO2 is N bonded to an O, double bonded, and an O. And of course we have our phenyl ring back here, and of course bonded here, positive charge and a negative charge here. So these electrons now are taken from the ring and onto the oxygen. So it's taking electrons from the ring onto the nitrogen. That's why it's called electron withdrawing group. As you can imagine, if we're pulling electrons from the ring here, which is already partially positive, it will be further destabilized here, and a slower reaction here, higher activation energy, less stable, to get here the product. So as a summary, for the Beckmann rearrangement, if we should have substituents such as X, if they're electron donating, it's going to make this transition state for the migration much more stable than much stabilized compared to the phenyl ring. And of course, if it's electron withdrawing, it's going to destabilize it. So here is a trend. OC2H5 will stabilize or migrate much faster, preferably compared to the OCH3. You may say, well, gee, we still have 2 electrons here and here, same here. But you will recall that the alkyl group are electron donating also. So we have an ethyl here and a methyl. So it's a more alkyl group here, or a longer alkyl group chain compared to a methyl. Here we have just a methyl. Notice no electron, no oxygen to donate into the ring. So we just have an alkyl group donating electrons just based on its inductive capability into the ring. So this is not as good as this one, but better than hydrogen. And of course, if you have electron withdrawing group, it would be even further down here. Okay, let's look at another type of rearrangement. And this one is called the Curtis rearrangement. Let's see what happens here. Here we have a ketone, 2 groups bonded to it. But instead of having here a oxime as we had before, we have the azide here, sodium azide. It's a salt, but let's look at it. It has here a nucleophilic end, and it has here an end looking like it could be a nitrogen gas. So what you can expect here, we look at the mechanism later on in the next slide, but let's just analyze what we think should happen. Since this is nucleophilic here, and this is electrophilic here, and of course partial negative, you can expect this reacting here. And once that reacts here, we have nitrogen here, which can come off as a gas, which makes this nitrogen here electron deficient once it bonds over here. So what I wanted to get here is just to get a good feel of what you think should happen, because you'll be asked to write the reaction mechanisms in the next exams and from here on. So you should have a good idea of what should happen. So here, electron deficient carbon, nucleophilic nitrogen can bond here, electrons will go out, and the product is here. So we'll have to justify this product based on the mechanism. You can see here that the phenyl group looks like it migrated to the nitrogen, and the methyl group remains bonded to the carbon. And of course, we have a good leafy group in the form of nitrogen gas. So let's look at the mechanism. So as I pointed out here, this is nucleophilic. So we have a pair of electrons, electrophilic right here. It comes in, these electrons go onto oxygen, a familiar mechanism that we've seen for the reactions of carbonyl. So here's what we have after this initial step here. So this proton protonates this nitrogen here to get this intermediate here. As you can imagine, this nitrogen is electron deficient. Why? Because it's bonded to another nitrogen, same electronegativity, but we have here a good leaving group in the form of nitrogen gas. So that's our nitrogen gas. Let me even emphasize it with a gas. As you know from undergraduate organic, if a reaction liberates a gas as a product, it's favored to go to the right because of entropy. So let's see what happens when these electrons come back in to form the very strong carbon-oxygen bond. There is a migration of a group. This one can migrate. We'll see in a second that this one can also migrate. But we know that this group here is better at migrating to an electron deficient nitrogen, We'll see in a second the same for the oxygen compared to the methyl group. So this is now the major product here, where the phenyl group migrates to the nitrogen as shown here to get that as the product, and of course nitrogen gas comes off. Let us look at an application of this. As I mentioned earlier, the Curtis rearrangement. I don't think I mentioned that, but this type of rearrangement is not the Beckmann. The Beckmann is for the oxime. This is the Curtis rearrangement for the azide. So we have sodium azide here. Again, you may recall that it's N plus and negative, and of course sodium. But the point is, we have a nucleophilic end here, as we expect. Let's just do what we expect first. We expect these electrons to bond here, and these electrons go up here. They would come back in. This would be an electron deficient nitrogen. This gas leaves. This nitrogen leaves as a gas, and we have a product. Notice this product here, though, is cyclic. So here's the nitrogen from the azide. So we have a ring expansion. So it implies that we have a carbon-carbon bond migration. So instead of an alkyl group or group migrating, we have a carbon-carbon bond, an entire bond that's migrating to create a ring expansion. And of course that migration is to the electron deficient nitrogen. So let's see how that happens. As you can imagine, nucleophilic nitrogen bonds to this electrophilic carbon. Electron goes onto the electronegative oxygen to form this intermediate. Not very stable. Well, it's an intermediate, but these electrons here can come back in. Well, we have an acid around, so we can protonate this nitrogen here to get that. So notice what happens here. These electrons come in to put another pair of electrons here to get this protonated. So we're looking like this, looks like nitrogen gas. Good leaving group, which means that this nitrogen here is electron deficient. So when these electrons come back in, we have a bond migration here. So this bond here migrates to the nitrogen, and this leaves as a gas. So this is a bond migration to the electron deficient nitrogen to get a ring expansion here. And of course, as you can imagine, as you can see, this is a cyclic amide here, or lactam. You may be wondering, could this bond migrate? Yes, it can. But since they are equivalent, or it's a symmetrical molecule here, either one migrate gives the same product. Let us look here at the electron deficient oxygen in terms of the reactions. The reaction here that we look at is known as the Baeyer-Villiger reaction. But let's see what happens here. We have a ketone with a phenyl again and a methyl. In this case, we are introducing here a peroxy acid, or a peracid, as an oxidizing agent. So we have here, it's an acid, so as you can imagine, this proton can protonate here, leaving the salt. So this salt here can react right here, and we have a good leaving group right here, as you can see here. So this nitrogen, this oxygen here, will become the electron deficient oxygen once it's bonded over here. So you can imagine a similar type of reaction as we had before, but in this case it's a oxygen. So let's see how this works. So let's look at the next slide. So here we have the ketone, electron deficient carbon. Since this is trifluoro peroxide, peroxy acid. It has a proton, so it's going to protonate here, as you can imagine, making this a better electrophile here. So the conjugate base of the acid, of the peroxy acid, which is here, attacks this carbon. Very similar to what we've seen before for the nitrogen, but in this case it's an oxygen. So it attacks here, and now you can see here's the leaving group right here, the trifluoroacetate anion, and here's the electron deficient oxygen right here. So when these electrons come back in to form the carbon oxygen double bond, there's a migration to the electron deficient oxygen, and this leaves. As we mentioned earlier, this is concerted, so it happens in one step, the migration as the group leaves. After that, we have here a minus this hydrogen that comes off, so we have here the ester that's formed, and of course we have here the leaving group that's formed here. So once again, so this comes in, so this proton here leaves, and we have here the ester, where this group here migrates to the oxygen. In other words, this group here migrates to the electron deficient oxygen that's coming in. And here it is. As we pointed out earlier, this group here could in fact migrate also to give a different product, but since the phenyl group is a better migrating group than the methyl, this becomes the major organic product here for the Baeyer-Villiger oxidation, or the Baeyer-Villiger rearrangement. Let's look at another example here. So here we have the same peroxy acid, in this case trifluoroperoxyacetic acid. Notice it's per acid because it has an extra oxygen. As you can imagine, protonation occurs here, then the conjugate base comes in here to create this oxygen as the electron deficient oxygen. Then we have a bond migration to this oxygen here, creating the ester here, and of course the leaving group. So here now you can see this is a cyclic ester, where there's a bond migration and a ring expansion. And you may recall that a cyclic ester here is unique, so it's as shown here. So let's look at the reaction here now that we have analyzed this product here. So let's go again. So here is the cyclohexanone and ester. The acid will protonate this to get this, make this even more electrophilic, which means that the nucleophilic peroxyacetate anion can attack right here to give this intermediate here. So this oxygen here is now the electrophilic, the electron deficient oxygen. As you can imagine, again, these electrons here come in to form the carbon oxygen double bond, and this bond migrates to the oxygen here, the electron deficient oxygen, and this group here leaves as the leaving group, and we have here our cyclic ester. Our cyclic ester right here is the product. Same aspect here. You can maybe asking, why doesn't this bond here migrate? And it can migrate, but since migration of this bond is equivalent to migration of this bond, they're the same, it results in the same product here, the cyclic ester. Let's look at another example here. So we have two products here. It's the same Beyer-Villiger rearrangement, or the Beyer-Villiger oxidation. You'll see it written sometimes as oxidation. Why? Because this is an oxidizing agent. The peroxy acid is an oxidizing agent, but it undergoes a rearrangement if it reacts with a ketone. So let's see what happens here. So as you can imagine, let's analyze what should happen before we look at the actual mechanism. As you can imagine, acid protonates the carbonyl here, and of course this acetate anion attacks here. One of these oxygens here will become the electron deficient oxygen, and of course now we have bond migration of this one or this one. So the question now is, which bond will migrate best? So one will give the major product. It appears that this migration here to the oxygen is the major product. So for some reason, more alkyl groups bonded to the carbon that's migrating is the major product. Of course, now you can assume why. More alkyl groups tend to stabilize the transition state, which is partially positive because alkyl groups are electron releasing, compared to the migration of this bond here, or this carbon here, over to the electron deficient oxygen that's in here, to get this as the minor product. So let's look here at the mechanism. So here, as you can imagine, starting off with the ketone, protonation from the acid, because it's an acid, gives this electrophilic carbon here. The acetate, the peroxide acetate anion, nucleophilic, will attack here to give this. Same mechanism. These electrons come back in, and we have a bond migration where this moves over to here. The electron deficient oxygen is right here, and we have our leaving group here, and we have our cyclic ester right here. This is the minor product, or been observed to be the minor product. Why? Because here we have a carbon that has two hydrogens here that are not good at electron releasing or stabilizing the transition state for that migration that we saw earlier. So this is less prone to migrate, as we'll see in the next slide, compared to this migration here, which has two methyl groups here. So again, you should be able to predict which bond migration should occur based on the stability or relative stability of the transition state for the migration. So let's look at the other one. Same starting material. Now we have protonation to give an electrophilic carbon here. The conjugate base, which is nucleophilic, attacks here to get this intermediate electron deficient oxygen right here again. Good leaving group right here. Now this bond migrates. Notice here we have a carbon here that's actually migrating over to here, but it has two methyl groups here that can stabilize the transition state for that migration much better than if it were just hydrogens. So this now becomes the major product here for this cyclic ester here. I think this is the last slide. Yes, it is. So once again, these are reactions of electron deficient nitrogen and electron deficient oxygen. They're very important intermediates in the synthesis, as you can see here, of cyclic esters and cyclic amides. So this brings us to the end of our section on reactive intermediates. So we have looked at radicals, we have looked at carbocations, we have looked at carboanions, we have looked at electron deficient nitrogen, electron deficient oxygen as reactive intermediates. Pardon me, we've also looked at carbenes. How could we forget carbenes? A very important reactive intermediates. We've looked at all those types reactive intermediates and how they react as intermediates to give final products. You should know the mechanisms of these reactions. The next set of lecture, the next section of this course deals with experimental tools that will be looked at to determine reaction mechanisms. These include linear free energy relationships and also kinetic isotope effects. You can start reading up on those. I'll get those lectures posted shortly. Okay, so continue studying hard. Okay.